When we first looked at linear equations, we took a look at this equation here, y equals 2x minus 1. And we plugged in some values for x, and we found the corresponding y's, and each x and y we could represent as a point on the chart. We saw that we could continue to pick x's and find the corresponding y's so that there were an infinite number of points on this chart. Together, these infinite points formed a shape, and that shape was a line. In this video, we're going to look at a new type of equation that forms a different shape on our chart. Let's consider this equation here. Y equals x squared plus 5x plus 4. This kind of equation, where we have an x squared term, this is called a quadratic equation. We're going to plug in some values for x, find the corresponding y's, and plot those points on the chart. I went ahead and made a little table here to organize some values for x and their corresponding y's. Let's bring out a chart and see what kind of shape these points make. We have x equals negative 5, y equals 4, x equals negative 4, y equals 0, x equals negative 3, y equals negative 2, x equals negative 2, y equals negative 2, x equals negative 1, y equals 0, and x equals 0, y equals 4. Each of these points is a solution to our quadratic equation, and if we connect the dots, we'll see that they form a curved shape, which we call a parabola. When we looked at linear equations, we saw that there were some important pieces to focus on, like the slope and the y-intercept. In a similar way, there are some important pieces of this parabola here that we need to focus in on. The first piece we want to focus on is these 2 points right here. These points are called the roots. This is where the parabola crosses the x-axis. The second important piece to consider with parabolas is this point right here. That point is called the vertex, and it is the lowest or highest point on the parabola. And if we draw a vertical line through the vertex, this line divides the parabola in half. You can think of it like we're cutting a sandwich. When you make a sandwich, you cut straight down the middle to create 2 equal parts of the sandwich. That's what we're doing here. This purple dotted line creates 2 halves of the parabola, and we call it the line of symmetry. So I mentioned that the vertex can be the lowest or highest point on a parabola. In this example, the parabola curves up, so the vertex would be the lowest point. We'll also look at parabolas that curve down. For example, we could have a parabola that looks like this. And in this case, our vertex would be the highest point on the parabola. Let's take a step back now that we've considered our quadratic equation and the parabola it creates. Let's ask, why is this kind of shape useful in the real world? When we took a look at linear equations, we saw that lines are very useful in the real world. Look around you right now. There's probably lines all around you. If you have a driveway, your driveway has a slope. The roads have a slope. If you're on a roller coaster, you have a slope as you're going up. So understanding lines can be very useful. But where do you see a curved shape like this? Well, let's consider our mini graph. Let's say you and your friend are playing soccer, and you're over here, and you kick the soccer ball to your friend. The soccer ball goes up, it gets to its highest point, and then it comes back down to your friend. So quadratic equations are often used to represent objects that are moving in the air. Another example is if you're playing fetch with your dog. You throw the ball, it goes up in the air, and then curves back down. So this kind of curved shape is useful to consider. When the parabola curves up like this, it's not as useful in real life. You don't really see that many objects that curve down and curve up like this. Maybe if you're digging a really weird hole. But the point is, these equations we're looking at, the linear equation, quadratic equation, and the one we'll look at in a future video, the exponential equation, these all have real-life applications. Let's continue our discussion of quadratic equations by taking a deeper look at the equation. Our example here is y equals x squared plus 5x plus 4. But what do quadratic equations look like in general? In general, a quadratic equation has the form y equals ax squared plus bx plus c, where a is not equal to 0. So a is either positive or negative. It can't be 0. The equation that we looked at above follows this format. It was y equals x squared plus 5x plus 4. And there's an implied 1 in front of the x squared. A couple important facts about this general form. If a is greater than 0, meaning a is positive, then the parabola will open up. So we'll have something that looks like this. And on the other hand, if a is less than 0, meaning a is negative, then our parabola opens down. And looking back at our discussion above, when we talked about the vertex, we said it's the lowest or highest point on the parabola. It's our pink dot. But we didn't talk about how to calculate where that is. So there's a useful formula for calculating the x-coordinate of that pink point, and then you can just plug that into the equation to find the y. So let's take a look at that equation. The x-coordinate of the vertex equals negative b over 2a. So now we're incorporating our general form of the equation. In this case, our b is 5 and our a is 1. So we just plug those into this equation. So we have negative 5 over 2 times 1. That gives us negative 5 over 2, and negative 5 divided by 2 equals negative 2.5. So we know the x-coordinate of the vertex is negative 2.5. Let's take a look at that on our graph. So we're saying the x-coordinate here is negative 2.5. And that makes sense, right? If you look at our line of symmetry, we're going right between negative 2 and negative 3. So negative 2.5 makes sense for the x-coordinate. So now for our pink point here, we have the x value, and we can go back to our original equation and plug it in to find the y. And when we do that, we find that our y is negative 2.25. So that is the location of the vertex. X equals negative 2.5, y equals negative 2.25. And when we figure out our x-coordinate for this vertex, we can also give an equation for the line of symmetry. If you recall, we looked at vertical lines like this when we discussed linear inequalities. And if you pick random points on this line, you can see that every single point has an x-coordinate of negative 2.5. So we say that the equation that represents this line of symmetry is x equals negative 2.5. So this equation says that our line goes through every point where x equals negative 2.5. For the rest of the video, we'll take a look at a couple quadratic equations and work on finding the vertex and the line of symmetry. In the next video, we'll focus on finding the roots. And one more thing before we move on. I'd like to take a look at this last section here. I realized I gave these rules here without really explaining them. So the question is, when a is positive, when it's greater than 0, why does the parabola open up? And on the flip side, when a is negative, when it's less than 0, why does it open down? Well, let's look at our general equation. Each time we plug in an x into this equation, this term changes, and this term changes. Our c at the end, it never changes. No matter what x you input, our c is just on the end by itself. So we want to see what happens to our first two terms when x gets really big, meaning as we go down the x-axis. Well, as x gets really big, our first term here gets super big because of the x squared. A big value for x squared becomes even bigger. Our second term would be smaller because we're just multiplying by x one time. So essentially, as x gets really big, our first term is going to be the biggest term. And x squared is always positive, and if a is positive, then that term ax squared is going to be positive. So looking at our graph, as x gets bigger and bigger, if our a is positive, then our y is going to be a really big positive. And the same thing happens on the other end. As x becomes a bigger and bigger negative, when we plug that into x squared, the same thing happens. A negative number squared is just a positive number. So it's same as the right side of the graph. And ax squared becomes a really big positive number. So essentially, as x gets really big or really small, our parabola will curve up because the corresponding y values will be very big positives. Don't worry if that's a little confusing. Feel free to rewind this and maybe pause to think through it yourself. And see if you can apply this same thinking to our second scenario. If a is negative and x gets really big or really small, what happens to y? Alrighty, let's move on to some examples. Find the vertex. And we're given the equation y equals x squared minus 6x plus 8. So this equation follows our general form of y equals ax squared plus bx plus c. So we know this is a quadratic equation. And when we plot a quadratic equation, it forms a parabola. And we're being asked to find where the vertex is. And it's the minimum case in this question because our a is 1. It's greater than 0. All right, we have an equation to find the x-coordinate of the vertex, and that is negative b over 2a. And if you're wondering where this equation comes from, it's kind of complicated. If you're interested, I'll include a video in the bonus material playlist showing where this equation comes from. But for now, we'll just use it to get to our vertex. And we know that our b here is negative 6, and our a is 1. So we can plug those into the equation. We have the negative of negative 6 divided by 2 times 1. As we've seen, the negative of a negative number is a positive number. So we'll have just positive 6 on top. And on bottom, 2 times 1 is 2. 6 divided by 2 gives us 3. So now we know the x-coordinate of the vertex. How do we find the y? Well, we just take our x-coordinate and plug it into our equation. So if the x-coordinate equals 3, then y equals 3 squared minus 6 times 3 plus 8. This gives us an opportunity to review our order of operations. So we'll put out our PEMDAS. P is for parentheses. We don't have any parentheses. E is for exponent. And we have our squared up there, 3 squared. M is for multiplication, and we have that here. D is for division. We don't have that. A is for addition. We see that plus sign. And S is for subtraction. We have our minus sign. Remember with PEMDAS, our order of operations, we move left to right. So let's focus on the E, the exponent. That is our 3 squared. So 3 squared is 3 times 3, which is 9. And we leave everything else the same. So our E is done. Next is the multiplication. So we have 9 minus 6 times 3 gives us 18. And then we have our plus 8 at the end. Our M is done. Finally, we have addition and subtraction. So these two work as a pair, just as multiplication and division do. Whichever comes first, we do that first. So in this case, we have a subtraction sign first. So we'll subtract first. 9 minus 18 gives us negative 9. And we have our plus 8 at the end. So we finish our subtraction. Now we have negative 9 plus 8, which gives us negative 1. Therefore, the vertex is at x equals 3, y equals negative 1. Let's go ahead and draw this parabola. Let's bring out a chart. There are a couple steps to follow to draw a parabola. First step, which we already did, is to find the vertex. We found that our vertex is at 3, negative 1, so we can plot that on the graph. And the vertex is important because it gives us the location of the parabola. We know the parabola is somewhere on this graph. It could be up here. It could be down here. But once we find the vertex, it kind of anchors the parabola to one place. We know that our parabola is going to sprout up like a plant from this point. So now we know the location of the parabola, but we don't know how wide it is. It could be really wide. It could be really narrow. So that's where step 2 comes in. To find the shape of the parabola, we can plot points on each side of the vertex. That'll give us some points on the left side of the vertex and on the right, and then we can draw a parabola through those points. Or the second way would be to find the roots. So looking back at our chart, the roots are where the parabola crosses the x-axis. So if we find those, we can draw our parabola through those points. As I mentioned, we'll focus on finding the roots in the next video. So for now, let's plot some points on each side of the vertex. Our quadratic equation was y equals x squared minus 6x plus 8. So we want to plug in points on each side of the vertex. So let's look at the left side. We can pick any x value. Let's pick 1. And plugging that in, we get 1 squared minus 6 times 1 plus 8. 1 squared is 1 minus 6 plus 8. 1 minus 6 is negative 5. And we have our plus 8. Negative 5 plus 8 gives us 3. So x equals 1 and y equals 3 is a point on the parabola. And here's a neat trick for plotting another point. Remember, there's a line of symmetry going through the vertex. So the point we just found is 2 steps away from the line of symmetry. The line of symmetry goes through x equals 3, and our point is at x equals 1. And that means 2 steps away on the other side, there's another point on the parabola. And 2 steps from x equals 3 gets us to x equals 5. So we know the point x equals 5 and y equals 3 is also on the parabola. So that saves some time. Every point that you find on one side of the parabola, you just flip it over the line of symmetry and you get another point. So we considered the line of symmetry before as if we were cutting a sandwich in half. Another way to think about it is every point on the left side should fold over onto the right side, like you're folding a piece of paper. So consider the point that we plotted here. If you fold it over the line of symmetry, like a piece of paper, you'd get to this point. So let's find one more point on the left side. How about we plug in x equals 2? Looking back at our quadratic equation, we have 2 squared minus 6 times 2 plus 8. 2 squared is 2 times 2, which is 4, minus 6 times 2, which is 12, plus 8. 4 minus 12 gives us negative 8, and we have a plus 8 at the end. Negative 8 plus 8 gives us 0. So when x equals 2, y equals 0. Do you notice anything? We just happened to find one of our roots. That point we just found is where the parabola crosses the x-axis. And this point is 1 unit from the line of symmetry. So if we fold it over the line, if we go 1 unit on the other side, we'll get to another point on the parabola. And since this point is on the x-axis, we just found our second root. So we were kind of lucky finding our roots this way, just by plugging in points. It's not always as easy as that, which is why we'll cover a couple methods in the next video for finding those roots. But now we have a couple points on each side of the vertex. So we can finally draw our parabola. And there we go, we have our parabola. First we found the vertex, which gave us our location. Then we plotted some points on each side of the vertex. And this gives us our shape. Those points we plotted help us see how wide that parabola is. Let's try one more example. Let's look at the equation. Y equals negative 2x squared plus 4x minus 3. This looks like it follows our general form, but let's check. We have y equals ax squared plus bx plus c. All right, that checks out. So we're looking at a quadratic equation. And once again, let's find the vertex. The x-coordinate of our vertex is negative b over 2a. In this case, b equals 4 and a equals negative 2. Plugging that in, we get negative 4 divided by 2 times negative 2. That leads to a negative 4 on top, and 2 times negative 2 gives us negative 4. Negative 4 divided by negative 4 gives us 1. So we have the x-coordinate of the vertex, and we can plug it in to our equation to find the y-coordinate. So let's do that. I'll bring our equation down here. So if our x-coordinate equals 1, then y equals negative 2 times 1 squared plus 4 times 1 minus 3. And we can write out our PEMDAS to work through this. We have an exponent, 1 squared. We have multiplication, addition, and subtraction. So we focus on the e, the exponent, first. Everything else stays the same. 1 squared is 1. And the e is done. Moving on to multiplication. We have that in 2 spots, so we can work on those left to right. Negative 2 times 1 is negative 2. 4 times 1 is 4. Our multiplication is done. Then we have addition and subtraction. Again, they're a pair. So we'll work on those left to right. -2 plus 4 gives us 2. And then 2 minus 3 gives us -1. So for our vertex, the x-coordinate is 1, and the y-coordinate is -1. So we can summarize that. Therefore, the vertex is at x equals 1 and y equals -1. Let's go ahead and draw a quick plot of our parabola. So we found our vertex. That's step 1 for drawing a parabola. It's at x equals 1, y equals -1. That gives us our location. And now we need to plot points on each side of the vertex to find our shape. Let's bring back our quadratic equation. So let's plug in a point on the left side of the vertex. And if you notice, there's one value that we can plug in that's really easy to calculate. That would be 0. Our x values get plugged in right here. So if we plug in 0 into each of those spots, our first piece becomes 0. It disappears. Our second piece becomes 0, and that disappears. And so all we're left with is our -3 at the end. So looking at our chart, if x equals 0, then y equals -3. It's just our -3 piece at the end. We saw a similar thing happen when we talked about linear equations. If you recall, our y equals mx plus b, when we plugged in a 0 for our x, this first piece disappeared, and we were left with our b, which we called our y-intercept. That's what we found here. We found the y-intercept for our parabola. We found where the parabola crosses the y-axis. And if we bring in our line of symmetry, we can find one more point. The point we just found is 1 unit away from the line of symmetry. If we fold that point over, we'll find another point. So that point is at 2, -3. And we can go ahead and draw our parabola. There's one more thing to note about these parabolas. Looking back at our quadratic equation, doesn't this piece at the end remind you of a line? It looks like mx plus b. It looks like someone started with a line, y equals 4x minus 3, and then they just moved it to the side and brought down this piece. And if you look at -2x squared, if you plug in a value for x squared becomes a big positive number. And then you multiply that by -2, and suddenly you have a big negative number. So this -2x squared is a big negative. So it's like we're starting with a line and then adding a big negative number to every y. What does that look like on the graph? Let's draw y equals 4x minus 3. So we have a y-intercept at -3. Our slope is 4. So we can rise 4 and run 1. So our quadratic equation here says we're starting with the line y equals 4x minus 3, and then we're adding a big negative to every y value. So wherever the y is on the line, it's getting smaller. Every single y that's on this line is getting smaller. Another way to think about it is this line is bending over. Every single point on that line is getting that big negative added to it. And doing that gets us to our parabola. So a parabola is just a line that we're bending into a new shape. I think that's pretty cool.